Hello and welcome back. My name is Ariel Rokem, and I am part of the core development team of DIPY. And I'll continue my lecture on automated fiber quantification. In the previous video, I showed you some results about the robustness and test reliability and reproducibility of results using tractometry. Now I'll tell you how to use PyFQ. So the full documentation is available at the website, at this website, github.io/pyfq. The PyFQ has two ways. There are two ways of using PyFQ, similar or mirroring the two ways that you can use DIPY, either using a Python API by writing Python code or using a command line interface. The inputs need to be organized. First thing you need to know is that the inputs need to be organized as a BIDS data set, the brain imaging data structure. BIDS describes how data sets should be organized so that they can be used by a variety of different tools. And what we require for PyFQ is inputs as a BIDS data set. The inputs need to have been pre-processed using some standard pre-processing. For example, you can use QSI prep or MRTrix or FSL in order to run things like motion correction, susceptibility distortion correction, and eddy current correction. Then once the data is organized, this pre-processed data is organized as a BIDS data set, then in Python, you can import the API module from PyFQ, and then you'll initialize an AFQ object by giving it simply the BIDS path, the path to the BIDS data set as a string. And then if you run myfq.plot track profiles, that will run through the entire processing pipeline. It will do the tractography, the modeling at the level of individual voxels, calculation of the tissue properties, the extraction of the bundles, and then the extraction of track profiles along the length of the bundles. And we'll plot that here. And it will also save out the output. So the output of the PyFQ is a CSV file that contains a table with tissue properties along the length of all the bundles and every individual. So you get one big CSV file that you can then import for analysis, further statistical analysis and other tools. I'll tell you about some of our tools in just a minute or two. And the documentation includes examples that show you how to do this using this AFQ API. So if you go to this website and to the examples and look at plot AFQ API, then you'll see how to use this Python API, including example data sets that we take from the example data sets that are available in DIPY, and we demonstrate how to use this in this example data set. Another way to use PyFQ is using a command line interface. In this case, you type PyFQ, that's the command line, and then you provide a path to a configuration file. And at the very least, this configuration file should tell you where to find the data set, this BIDS data set. And if that's all you provided as information in there, that's fine, and the rest will just run using the default methods. But as I told you in the previous video, the software is highly configurable. You can configure it to use a variety of different methods at every stage in the pipeline. So you can set that by writing different options within this config file. You can generate a config by a default config by using the generate config only argument or flag in the PyFQ command line interface. And that will generate a TOML file with the default config that you can edit to match what you need. So that's how you use PyFQ. Next, what I'd like to tell you is about visualizing and sharing this kind of tractometry data. So some of the challenges that we face when we do this kind of work, especially with very large data sets, it's hard to interrogate these data sets, hard to explore these data sets. And then it's really hard to share the results from a study where you collected data. Our solution to that is called AFQ Browser. It's a web browser-based visualization tool that visualizes tractometry data. There's a command line interface for that builds the app and uploads the website into GitHub as a website on GitHub that includes all of the data and that you can then explore. There's an example available here from a study from Sarka et al. From 2017 that you can explore. Let me show you what that looks like here in a short video. Play that. So So you can see this is the website that I went to. This is the Sarika data set. And what you can see here is there's a visualization of the different bundles, and you can explore that visualization and resize it. And then you can choose, for example, here I've chosen the left corticospinal tract and the right corticospinal tract. And you can choose different tissue properties. Here I'm going to use the fractional anisotropy. This data set contains a group of patients with amyotrophic lateral sclerosis, ALS. This is a disease that affects motor neurons. And so we see differences between these groups in the corticospinal tract. So here, if we sort the data by whether these are controls or patients, you can see that the FA profiles diverge from each other. And then you can continue to explore. You can ask where in the anatomy is the difference most significant, most salient. You can do that by brushing onto these tracks. So here we're selecting the part of the track, the part of the bundle that has the largest difference. And in the anatomy, meanwhile, what you can see is that the anatomical portion that is most affected by ALS is the one that is they're highlighted in the anatomical view. So you can see where along the length of the tract is the largest difference. Okay, in addition to visualizing the data, what you'll see is that when I create such a website, there's also a couple of buttons down there that allow visitors to the website to download then the subject metadata and the bundle profiles, again, in CSV files that can then be loaded into subsequent analysis. I'll also mention that if you click on this button at the top right, that will take you to the Binder website, where you have Jupyter notebooks that you can be used in order to explore these data even more. So this opens up the possibility for further exploration of the data in a different, using code inside of the Jupyter notebook. Okay, to install FQ browser, you would install that using pip install FQ browser, and then the 3 command line ways to use this is FQ browser assemble, which you provide the outputs from PyFQ to, and then it builds this website for you. Then you can run it so that you can see this on your own computer, run it locally on your own machine. And FQ browser publish would then upload your built website up into a repo on GitHub so that others can see it as a GitHub Pages website. Okay. I'll stop here, and in the next video, I will discuss how we use machine learning in order to provide insight out of these data sets.